Thank you for the introduction. So first, I just want to show you a little bit about the background to my research. So this is a chart that is presented by NREL occasionally. And it charts the progress of each technology in solar cell research. So you can match, or so you can watch the efficiency as the years go on. And as you can see, many decades go into a lot of these technologies, in some cases over 30 years. But you can see that for most of them, it's a very steady increase in efficiency increase. However, if you look in the bottom right corner, the yellow dots with the red accent around it are the Perovskite solar cells. So these, as you can tell, are very rapidly increasing in efficiency and have only been around for a few years. So that's very exciting, and that's why it's such an exciting field of research to work in. But what are Perovskites? So this is a Perovskite structure. In this case, we're using lead iodide octahedra. So that's what this lead iodide octahedra. So there's a lead in the center of this octahedron with 6 iodides around it. And each adjacent lead will share one iodide, which is the corner of those octahedra. So that's why we share. That's why we say it's corner sharing octahedra. And then this will form a 3-dimensional framework in all directions, and it's negatively charged. So to balance that charge, you need a methylammonium cation that resides in the cavity. This material is very nice. It has a very good band gap for solar cells, around 1.6 eV. And it's a direct band gap absorber, which means that it has it absorbs a lot of light for a very small amount of material. So because of that, you can form thin film devices. And so this is an example of an architecture here for a device. However, it's not perfect. There are some concerns that we have to address before we move forward with it. One is the toxicity of the lead, especially for a material that is slightly water soluble. And then the stability of the material, both to light and to moisture. So the light issue, Hema talked about earlier, we could see segregation of iodide in the material, potentially decomposition. We don't really know too much about that right now. The moisture stability, though, is really apparent in the laboratory. If you leave a film out, it'll convert fairly quickly. One other issue, mostly for research purposes, is the consistency of the film formation. Many labs have their own techniques that they report. However, it's really hard to reproduce those. And so if we could come up with a material or a technique for deposition that's easy for everyone to do, that'd be really, really helpful. So with that in mind, I'd like to introduce to you a different class or a different type of material that's very related that we call the layered perovskites. And so this here on the left is a very typical example of a layered perovskite. We still call it a perovskite because it's corner sharing octahedra, in this case of lead iodide octahedra. But because we're adding in larger organic cations, we're separating different layers of that material, so we actually get a layered structure. This, however, is just one of many types of layered perovskites that we like to call the N greater than 1 structures. And so the N value here is essentially counting the number of lead iodide octahedra in each sheet. And so I showed you before the N equals 1. However, the N equals 2 and 3 are shown here as well. And hypothetically, you could get any structure you wanted. In reality, it's pretty hard to get some of the ones with higher N values. But if you take this to the limit, you eventually get out N equals infinity, which is actually just the 3-dimensional structure that I talked about before. So these materials, the layered materials, are really nice because you're adding in this organic molecule. And you can imagine adding any functionality you wanted into that material just by using organic chemistry to put anything that fits inside of the structure. So the layered perovskites also tend to have different properties. For example, something very important to solar cells are the band gap and the exciton binding energy of these materials. As you go to smaller N values, you're reducing the dimensionality and therefore reducing the size of that box. And you're increasing the band gap of the material. Also, the exciton binding energy increases. So therefore, when you create a hole and electron pair in the material, it's much harder to separate those and do work using the device. And so we decided to explore the N=3 material because this is a nice intermediate between the two extremes. You still get something that approaches the three-dimensional material, hopefully in its electronic and optical properties. However, you still get to use the layered structure with the larger organic molecules, and therefore you can add in any functionality you want into the material in the future. So I was able to synthesize this material shown here. This is a crystal structure that we collected and solved ourselves. It is phenethylammonium, methylammonium, lead iodide, the N=3 perovskite. Like I said, it retains a similar structure to the three-dimensional perovskite, and will hopefully then have the same or very similar properties. It is solution processable like the three-dimensional material. However, in this case, it's actually easier to make films out of this material, both because of the layered structure, allowing you to spin the material down on a substrate more easily, but also because you can do it in ambient conditions, which is nice. And after you make the film, it is also more stable to moisture than three-dimensional material, and I'll talk about that later on. But some things to consider, like I said, these layered materials have larger band gaps, which means you're absorbing less of the spectrum. We think this material might actually be better for a tandem device. And then another thing that we hope to address in the future is a possibility of limited carrier transport, mostly in the vertical direction in that figure. You can imagine it might be hard for a carrier to hop from one sheet of lead iodide octahedra down to the next. So making films of this material is very easy. We use a single-step solution spinning step from a 1 molar lead concentration in DMF. Shown here on the left is an SEM of the N=3 material, and it's really hard to see much because it's really flat. But if you try and do the same technique with the 3D perovskite shown there on the right, first of all, you need to anneal it to actually form the material. So that's one step that's extra. But also, even when you do that, there are holes all over the film, which is not good for a thin film device. You can make nice films with the three-dimensional material. However, they are much more difficult. There are a few reported out there that I'll mention briefly here. You can start with a lead iodide film, PBI2. That has to start out like as a very nice film. And then you convert it at high temperatures using methylammonium vapor. You can also add a polymer to the solution spinning step. Or even you can do a co-evaporation shown here on the right, which is where you have very high temperature sources of PBI2 and methylammonium iodide that in the vapor phase under vacuum will condense on your substrate. If you want to look at any material as an absorber in a solar cell, you need to know the optical properties. There's a few things you can get out of these types of measurements. One is the band gap of the material, or at least an estimate of it. Therefore, you will know where in the solar spectrum it will absorb. But you can also get an idea of the relative energy levels in the material beyond just the band gap. So I'll talk about a little bit about that. In blue on the left is an absorbance spectrum of the three-dimensional perovskite, methylammonium lead iodide. That one will absorb around its band gap, around 1.6 eV, and all the energies above that. My material, because it has the higher band gap, does not absorb until higher energies. But interestingly, we're seeing peaks in the spectrum in red there. And on the next slide, I'll talk about what I think is going on. But we've been able to identify these as the N=1, 2, 3, 4, and 5 materials of the layered perovskites. So that was interesting to find there. The photoluminescence shown there on the right is important to know. The blue scan, which is the methylammonium lead iodide 3D perovskite, happens where is reported in literature at around 1.6 eV. My material, the photoluminescence occurs at a slightly higher energy, around 1.7. So this is significant because you were getting a higher energy photoluminescence, which is what you would expect from a higher bandgap material. However, this photoluminescence is not actually occurring from the N=3 material in the film. So we think this is actually a lower energy material in the film where all the carriers are collecting there, and then photoluminescence is occurring from that material. We do think it probably still is a layered perovskite, but it's not exactly the layered perovskite that we were searching for. So this is what we think is actually happening during film formation. Once you deposit the film down, we have large domains of n=3 material, the blue octahedra up there. And these are large domains that will diffract X-rays. So we were able to take X-rays of these materials and confirm that it is exclusively by X-ray n=3 crystalline material. However, defect layers of the n=1, 2, 4, and 5, defect layers are in the film. And because they're scattered and randomly distributed throughout the material, you will not see them in the X-ray diffraction because there's not enough unit cells to diffract from. However, they will still have light passing through them, and you will see the optical properties from those layers. Importantly, this material is stable to humidity, both during the deposition but after. So here I've shown a methylammonium lead iodide perovskite film that has been exposed to 52% relative humidity over 46 days. And even after 4 days, you see it's starting to convert into PbI2, lead iodide. And after 46 days, it's actually almost fully converted. However, if you take my material and do the same experiment, after 46 days, it's essentially unchanged. This is very important for solar cells, both during the fabrication and after. You can imagine it would be a lot cheaper for a manufacturer to make a solar cell lineup of roll-to-roll that is under air rather than under nitrogen. And finally, I was able to make devices. So this is essentially copying what's done by some people in the literature. It's essentially a titania compact layer, which is your N-type material, followed by the perovskite, your hole conductor, which is an organic polymer, spiro-omitad, and then gold. And you'll get light to go into the layer of the perovskite. You'll get your hole and electron pair, and then you will extract those into the titania for the electron and the spiro-omitad for the hole. To test these devices, we took IV curves. Essentially what this is you are sweeping the voltage and measuring the current response when you're illuminating the device. So what you want to see, as I've plotted it here, you want to see high voltages, so out to the right, and you want to see high currents, in this case negative currents, so down to the bottom. Importantly, this material has a high VOC, which is where it crosses the x-axis. It's around 1.18 volts. This is a full 100 millivolts higher than a record cell for methylammonium lead iodide. And in fact, most of those cells will actually be closer to around 1 volt. So this is a higher VOC. We're getting a pretty good JSC. So JSC is the short circuit current, which is at the y-axis. This is essentially a measure of the photocurrent in the device. It's certainly limited when you compare it to the 3D perovskite, but we think it's very good for a first try. And we think that increasing that short circuit current or the photocurrent will allow for better devices in the future. And because of that slightly smaller photocurrent, we are getting an efficiency that's lower than 3D perovskites, just under 5% at around 4.73. But we think hopefully in future generations we can improve that. So with that, I'd like to conclude by reiterating that I was able to make this new material. I didn't say this before, but this is the first n=3 lead iodide perovskite ever reported. We were able to test the humidity stability of this material, and we show that it is much more robust when you expose it to a controlled humidity environment compared to the 3D perovskite. But also, putting it in a device, it performs very well, especially as a first-generation material, getting almost 5% efficient conversion of the solar energy. So with that, I'd like to thank GCEP for letting me speak today, and for funding. I'd like to thank my PI, Hema, everyone in our group, but specifically Diego, Emma, and Matt for their help on this project, and then Professor Michael McGee, and then his group, specifically Eric, William, and Gray. And with that, I'll take any questions. Yeah.
Hey, did you make more than one of these devices?
Yeah. I made a fairly large batch, a couple different batches, but close to maybe like 20 cells, devices.
Of each one?
So the illuminated area is around 0.12 square centimeters. The full devices are closer to like 1.5 square centimeters.
Okay. And did all of them show the behavior that you showed in the IV curve? That is, the point below the fitted line, just below max power voltage?
Yeah, so I didn't have time to talk about this, but these devices are very hysteretic in the JV curves. So if you measure one direction versus another, you'll get a different JV curve. So I've tried to correct for that by doing very slow measurements, essentially holding at one voltage, measuring the current until it levels off, and then moving on. In this case, I did do that, but I didn't hold it for long enough at those near the max power point, and so it didn't level off completely, so that it's not exactly the current that you would actually get at that voltage. Most of the devices that I did make did show that, though.
Thank you.
Mm-hmm.
Hi, Ian. I'm just wondering, from the absorption, can you estimate the relative abundance of the impurity n=1, =2, and 4 phases, and then can you get some sense of the average domain size of the n=3 from the X-ray? Because in your cartoon, it seemed to imply that you just had you had n=3, and then an n=1 impurity, and then n=3, and then another impurity. I guess the alternative would be that you have very large n=3 domains, and then a region where it's 1, 4, 2, where all of your impurities are kind of jammed into one section, and then another large. So I'm just wondering if you can distinguish those.
Yeah, I think it might be possible to quantify it using UV-Vis absorption. We weren't able to do that, especially because those higher n values, even starting with n=3, are not very well characterized. The literature of the n=1 and 2 is fairly well known, more n=1 than n=2. But there are absorption spectra of pure n=1 material and 2 reported. The larger n values, it's really hard to make them in pure phase. We were able to crystallize the n=3, but in fairly small amounts and not really enough to do many quantitative measurements on. I think powder X-ray diffraction to get the domain size of the n=3 would also be possible, but it's very difficult, mostly because you have to form these as films. I have done some larger films that I've been able to scrape into a powder, which is essentially the only way to get a completely unoriented scan. However, it's just hard to get enough material to get a nice scan. I think one of the better powder X-rays I've gotten from these materials was a really long overnight scan on a very small amount of powder. I think potentially, but we weren't able to.
Do you think it matters with respect to your device performance?
I think it does, definitely. I think we're stunting the VOC of this material, these devices, because we have those lower energy materials in there, the impurity phases. If we had exclusively n=3, I think we would be able to bump the VOC up quite a bit. I think the current density, I don't really know if that would be affected too much, because we might see a loss in current density possibly from those lower energy materials, which might actually have better carrier transport. But yeah, we don't know for sure. I think it's possible that we would increase or decrease that. I don't know.
Cool. How much does the series resistance increase from the bulk to your layered three-layer structure?
The 3D perovskite, are you talking about the 3D perovskites?
Yeah.
Yeah. So those devices, most people can make them such that the series resistance is pretty small. I don't make those devices. I don't think I've ever made a complete device out of that material.
Does your cross-plane connectivity decrease because you're basically cutting off the conduction pathways?
Yeah, we do think we are limiting the current or the mobility in that direction specifically. I did collect an EQE spectrum and an IQE, and we do know that we're not getting all the carriers out that we generate, and we think that's probably because of the limited carrier mobility. So yeah, I think it's it's coming from that, likely.